This video is about rotational motion. If we imagine a child running onto a merry-go-round, when the merry-go-round turns, it is rotating about its centre of mass. And that's an example of rotation. We've been considering different types of motion. We've looked at translational or linear motion, and that's where it moves in a straight line. We've considered circular motion, where it moves round in a circle. But now we're going to consider rotation. Rotation is where it spins on its own axis. So let's look at the definition. Rotation is the turning or rotation of a rigid body about its centre of mass. And here is a picture of a star, and I'm going to rotate it. Now, hopefully you saw as it rotated, I've put two dots on it. The red dot moved round in a small circle, and we had a blue dot, and the blue dot moved round on a much larger circle. And this is one of the problems when we're trying to analyse rotational motion. The distance moved by different parts of the body is different. The red dot moved a much smaller distance than the blue dot, yet both are on the star that was rotating. So we need to look at this a bit more carefully. Let's have a look at just a quarter of a turn. Here's a quarter of a turn. Now you will have noticed that the blue dot moved from and around on that angle. But if we look at the red one, it only moved around that distance. And you can see that the distance moved is different. But hopefully you can also see that the angle turned is the same. Now, that helps us analyse rotation. We're going to analyse rotation in terms of how much angle is turned. So let's have a look at this. What angle are we going to use? Well, we're going to measure our angle in radians, and to do that we need to define what a radian is. Now, the radian, according to the definition, is the angle subtended at the centre of a circle by an arc equal in length to the radius. So what does that mean? If we look at the diagram here, if the length d around the circumference of the circle equals the length of the radius, then the angle turned to theta is 1 radian. And that's the definition of a radian. And we're going to use that to define how far things turn for rotation. We call the amount that it turns angular displacement, and we give it the symbol theta. It's the angle turned in radians. And we've got a connecting formula between the distance of a point round on the edge with the angle turned. So the distance moved, or the displacement, in meters equals theta, which we call the angular displacement, in radians, where r is the length of the radius. And that, of course, is measured in meters as well. So that's the link for angular displacement to the displacement of a point round the edge. We can look similarly for angular velocity. Angular velocity, we use the symbol omega, is how fast it turns in radians per second. And that is linked to the velocity in the same way as before. So the velocity in meters per second to the angular velocity in radians per second is linked by the radius, measured in meters. We also have angular acceleration, alpha, and that's the rate of change of turning, and it's measured in radians per second. And that's linked to the actual acceleration of a point on the edge. Acceleration, measured in meters per second squared. Angular acceleration, in radians per second squared, again, is linked by multiplying by r, as you can see in the equations. The linear acceleration is still towards the center, just like with circular motion, and the linear velocity is still tangential to the circle, just like in circular motion, the linear velocity is the same way. But now we have two other things. We have angular velocity, which is omega, and angular acceleration, which is alpha. On this page, I've summarized what I've said on the previous sheets. It's probably worth you pausing the video at this point and copying this information down so you have it readily available. Now, we've defined the equivalent definitions for rotation as we had for linear motion. Namely, we've taken displacement, which was d, and we've now got angular displacement, which is theta. We've taken velocity, v, to angular velocity, which is omega. And we've taken acceleration, which is a, to angular acceleration, which is alpha. So that's what we've done. Having done that, in the same way that we did for linear motion, we can use either graphical analysis or calculus to produce equations of motion for rotation. Now, we don't have to learn how to do that, but we do have to be able to use the equations that are formed. And these are the equations that we've got. You will see, if you look carefully, they are very similar to the linear ones. All we've done is written omega f instead of vf, omega I instead of vi, alpha instead of a, and theta instead of d. T actually stays the same, so that's the nice simple one. These can be used in the same way for rotation as the linear equations of motion can be used for translational motion. We just use them the same way. Note, to convert revolutions per minute into radians per second, we multiply by 2 pi. 2 pi is the number of radians in a circle, and then obviously to convert minutes to seconds, we have to divide by 60. That's the first video on rotation.